You're in the forest when there's an invasion of snails, and you want to get out of there as fast as possible. You decide to escape to a beach nearby, but the issue is there's multiple paths you can take to get there. How do you figure out the shortest amount of time you can take to get to the beach? Here's our map. Each intersection is denoted by a node labeled A through F. Intersections are special because we have a choice of taking a new street. Here we label the time it takes to get from node to node, because without this information, we can't make an accurate estimate. So we have all of this information, but there are some trees getting in our way, so let's draw it and simplify it a little bit. As you can see, we're showing intersections or nodes as dots and roads as lines. Now let's get to the algorithm. To find the shortest time, we have to keep track of a few things. First, we need to know the current node that we're looking at. Second, we need to know which nodes we've already looked at so we don't look at them again, because that would be inefficient. Last, we need to have a list of all of the nodes and the amount of time that it takes to get to them from the starting point. Because we don't know how long it'll take to get to each node, we use infinity as a placeholder. We also know that it takes 0 minutes to get to A because A is your starting point. From A, we can visit B, C, and E. To get the time values of B, C, and E, we simply add the time value of A, which is 0, and the time it takes to get from A to that node. So, for example, for A to C, it would be 0 plus 5, resulting in a time value of 5 for C. Now that we've considered the travel times to its adjacent nodes, we can say that we visited A, meaning that we have the value for the shortest time to get to A, and we've considered all of the roads leading out of A. The node that we consider next is the node with the shortest time value that hasn't already been visited before, which in this case is C, because 5 is the smallest assigned time value remaining. Again, we check the nodes adjacent to C, which are A, B, and D. We don't have to worry about A because it's already been visited. For B, we add the value of C and the distance to B, which is 7. This is greater than the current value of C, so we don't replace it because that would mean assigning B a path time that isn't the fastest. To find the value of D, add the value of C, which is 5, to the distance to D, which is 3, and this totals to 8. Since 8 is less than infinity, we replace it. Now we can say that we have visited C and we have the shortest time value to get to C. Now, the next smallest node that hasn't been visited is B. From B, we can get to A, C, and D. But since A and C have already been visited, we only need to check the value for D. The value of B, 6, plus the distance to D, 12, totals to 18, which is greater than 8, so we don't replace the value of D. Now we can say that we visited B. The next smallest node is D, which is adjacent to C, B, and F. Since C and B have already been visited, we only need to check the value for F. The value of D, 8, plus the distance to F, 2, totals to 10. Since it's less than infinity, the time value of F is replaced with 10, and then we are done with D. Now, the node with the smallest time value is F, and F is where we want to end, because it leads us to the beach. In the end, it takes 10 minutes to get from the forest to the beach.